I will present the latest result of the Sund31Jan C1 mission devoted to the study of the seismic phenomena from space, as well as other physical quantities related to ionosphere and magnetosphere. I will present that on behalf of the Sund31Jan C1 mission team. I will start with the current state of the Sund31Jan mission. I will overview the CSS cooperation activities and the outcome of this cooperation, in particular validation of the result in the first scientific results. The Sund31Jan mission is named after the ancient scientist Sund31Jan, who invented the world's first seismoscope. It is aimed to detect the geophysical fields of near-Earth space. It is planned to launch a series of probes in following decades, in particular the Sund31Jan 1, which is a series of electromagnetic satellites, the China Seismo-Electromagnetic Satellite CSES. The first has been launched on February 2nd, 2018. The second one is under development, and the third one is going to be a constellation, which is planned for the coming years. And then the second series Sund31Jan satellite are gravity satellites, which are still in the proposal stage to study gravity anomaly around the Earth. The current status of the CSES satellite, the first one which has been launched in 2018, is operating at an altitude of around 7 kilometers on a polar orbit. The status of the platform is that the position of the platform is very stable. Is orbiting over most of the belt track, covering this area on the Earth very, very systematically. The working mode operates perfectly, meeting ground design, has a good cleanliness of the control in the various quantities, and has a very well-defined charging potential, which is stable with time. The satellite is equipped with state-of-the-art scientific payloads, which are able to measure the different quantities which are characterizing the magnetosphere and the ionosphere environments. Starting with the high-precision magnetometer, HPM, which are 2 flux gate plus 1 coupled dark state magnetometer, which is operating between DC to 16 Hertz. Continue with another search coil magnetometer, SCM, operating between 10 Hertz to 20 kilohertz. We then have an electric field detector, EFD, from DC to 3.5 megahertz, a very sensitive detector for electric field, oscillating electric fields. A plasma analyzer package, PAP, which is measuring ion density from 10 to the 2 to 10 to the 7 per centimeters cube, and ion temperature at 500 to 10,000 K, an ion content between H+, helium+, and O+, and ion drift velocities. We then have a Langmuir probe, LAP, measuring the electron density of 10 to the 2 to 10 to the 7 per centimeter cube, and electron temperature between 500 and 10,000 K. A GNSS occultation receiver, GOR, which is measuring the TEC, including the air refraction index, profile of the air temperature and pressure, and ionospheric scintillation index. Then we have 2 detectors devoted to measurement of high energy or low energy ionized particles, individual particles. One is HPP, measuring proton flux between 1.5 MeV to 200 MeV, and electron flux above 100 keV. And then we have the energetic particle detector built in Italy with the collaboration with the Italian Space Agency and INFN, measuring proton flux between 30 and 100 MeV and electron between 30 and 200 MeV. Altogether, this set of payload create a very powerful instrument to measure all the significant variables characterizing the magnetosphere and the ionosphere. The CS2 will have a similar configuration as CS01 with a new ionospheric photometer. And it is now in phase of construction. In 2022 will be launched. And the CSC3 constellation is a project which is in a phase of demonstration and preparation. to be approved in the coming years. The content of my talk will be the continuing with overviewing of CSCS cooperation and collaboration activities. First of all, we had to validate and the data quality of the various quantities, starting with the various satellite stability and telecommunication characteristics. In order to ensure that we were in very quiet magnetic and electric condition, we had to process various data about the magnetic field in different conditions. And we were able eventually to find operating conditions which were very much compliant with the specification of the satellite and the various instruments. The result of that is that CSCS now can contribute to the global geomagnetic field model, providing very accurate measurement of the magnetic field density, both providing declination and inclination map, and are in perfect agreement with the existing data and modeling. So these data will be contributing to the next generation of magnetic field map, geomagnetic field map around the Earth. The accuracy of the magnetic field measurement also allow us to study anomalies at the regional level, in the regional lithospheric magnetic environment. And we were able to find a number of high magnetic anomaly areas in China, and one low magnetic anomaly area in the southern Himalayan Tibetan plateau. And this observation helps understanding the background for the magnetic condition observing from space. All the scientific results of the magnetic measurement are about how this is modulated during storm time. And this has been studied both using data in the North Hemisphere on the night side, as well as confronting that with the data collected by other satellites or derived from the statistical model based on CHAMP data. And we found a very good agreement between those observation of CSCS and measurement or modeling by other instruments. We were able to perform validation also on other payload, like the electromagnetic field detector, comparing the observation of CSCS to Demeter, and finding a good agreement between the electromagnetic field measurement by the two satellites, as well in the simulation. And this is a result which has been published on the Journal of Geophysical Research. And this validation of EFD data was also possible at the VLF to HF band between 18 kilohertz up to 3.5 megahertz. This kind of correlation and studies allow us to observe 4 wave structure of these signals corresponding to the electron density recorded by the LAP. And this has been is subject of a detailed study which is going to be published soon. The capability to record electric and magnetic field we allow us also to study the presence of Whistler waves due to lighting, as an example. We did that using an artificial intelligence algorithm based on the deep neural network to detect those Whistlers, and we were able to have a detection accuracy higher than 99.9%. And so this technique was eventually integrated into display system, and which is very efficient in determining those kind of phenomena. as an example, in this chart, we can see the location of the detector Whistler. The red data are the data orbit, and the blue dots are the location where the Whistler have been observed. We also made a validation between CSCS and SWARM on the plasma parameter observation. This validation was very positive, both on the intensity as well on the variation on the various quantity, in particular the NE over TE, which is very similar to prediction, and also the global distribution with some small adjustment between CSCS and SWARM. And this is also the subject of a publication of the two groups together of this cross calibration between the two detectors and the two satellites. We then went to calibrate and validate the ionospheric plasma measurement, the Langmuir probe, and the GRO. This analysis was showing again small-scale structure, which are compatible with what has been observed by the SWARM satellite. So this cross-calibration was also very effective in confirming that the observation by CSS was coherent, consistent with the observation by SWARM. And also we are able to measure the Langmuir probe data during an annular solar eclipse, and we were able to study the behavior of the properties of the plasma during the solar eclipse, as well as before and after. And the observation by the Langmuir probe by CSCS is very similar to what has been observed in this occasion by SWARM. So again, a confirmation that the good performance of the Langmuir probe for such a very peculiar phenomenon as a solar annular eclipse. And using the TEC data, we were also able to do ionospheric occultation analysis and comparing the data collected by CSCS with the observation by COSMIC, and having a correlation that has been shown very well correlated between these two satellites. So CSCS will be also able to operate this TEC analysis through the atmosphere to analyze properties of the atmosphere using this technique. We then did a number of calibration and study using the energetic particle built by China and Italian Space Agency with INFN, the Institute for Nuclear Physics. It is two payloads, the HEPP built by China and the HEPD built by Italy, and they are covering two complementary energy intervals. This is an example of the validation of these two particle detectors using electron and proton, mapping them over the various orbit. So we can see clearly that the South Atlantic anomaly is observed by the two detectors. This is measuring the flux of those charged particles, charged electrons. Of course, the shape is different because the energies of those two detectors, the energy coverage is different. In the lower energy of the Chinese detector, we clearly see the presence at a high latitude of measurement connected to the Van Allen belt. Those measurements are present also at higher energies, but the intensity is much smaller. And during storm time, we can study the variation of these distributions of charged particles, and this in particular has been done during a storm which took place at the beginning of August with respect to the other part of the period in August 2018, which was quiet, and we can clearly see the connection between the fluxes variation and the arrival of the storm. Using this kind of low energy particle, we can study a number of processes. As an example, the chorus acceleration of relativistic electron in extremely low L shells during geomagnetic storm, as we can see on the left plot, or electron filling and proton loss in irradiation belt and changes in the characteristic, the South Atlantic anomaly during the same storm in August 2018. So those two detectors are very sensitive to study stability, but also variation of low energy particle trapped around the Earth. This is an incomplete list of collaborating scientific papers which have been published in the last 2 years. Many more are in progress, and this collaboration is proceeding very well, also in preparation of the new CSCS-2 satellite to be launched in 2022. And with this, I thank you for your attention. I wish you a good continuation of this interesting conference.